We use batteries every single day. And almost everyone, including plenty of textbooks, pictures them wrong. Electricity does not flow through the inside of a battery. Not one electron ever crosses it. And yet, every time you use it, a current really is flowing through. So what exactly is moving in there? Today, we shrink down and simulate the invisible world inside a single cell to finally see what's really going on. This is our cell, the one we will study for this entire series. It has 3 parts. On the left, the negative electrode. On the right, the positive electrode. And soaked through everything in between, a liquid called the electrolyte. Connect a wire and a light bulb across the 2 ends, and the battery comes alive. Now here is the one rule that changes everything. That electrolyte in the middle is an electronic insulator. It flatly refuses to let a single electron pass through it, but it is an excellent ionic conductor. Charged atoms, ions, slip through it with ease. Why the difference? The electrolyte is just a salt dissolved in a solvent. It has no free electrons and no metal pathway, so an electron trying to cross finds nothing to travel on. But the salt itself has split into charged ions that are free to drift. So the middle of the battery is a wall to electrons and an open road to ions. That single fact kills the naive picture. Electrons cannot loop round and round, out through the wire and back through the middle. The middle is a dead end for them, so if a current still flows, something else has to carry charge across that gap. And it does. Here is the real chemistry. At the negative electrode, an atom gives up 1 electron. What is left behind is a positive ion. We call that oxidation. At the same instant, over at the positive electrode, an ion and an electron are accepted back in. That is reduction. One electrode lets go, the other takes in, and that imbalance is what pushes everything into motion. Now follow the 2 pieces that just split apart. The electron cannot cross the electrolyte, so it takes the only path it has, out through the wire, through your device, and around to the positive side. The ion cannot travel down the wire, so it takes its only path, straight across the electrolyte, through the inside. Think of a couple leaving a concert. One takes the highway, the other takes the train. Different routes, but they arrive together. 2 carriers, 2 completely separate roads. Electrons on the outside, ions on the inside, both meeting at the same electrode. Let's watch it happen in a real simulation of our cell. As it discharges, positive ions stream through the electrolyte, from the negative side to the positive side. And watch the electrolyte itself, because a hidden field appears. Where ions crowd in, the concentration climbs. Where they leave, it falls. In our simulation, it starts uniform at 1,000, then swings up past 2,000 on one side and down below 500 on the other. You could never see this in a real cell, but it is always there. It is the first of many invisible fields we will uncover. And on the outside, at the same time, the electrons are lighting the bulb, and the cell's voltage slowly sags, from about 4 volts down toward 2.5 as it empties. Every number on that voltage line is being set by what the ions are doing inside. One honest detail, because this is a course, not a cartoon, it is not only the positive ions that move. The electrolyte also contains negative ions, and they drift the other way. Both help carry the current through the liquid, but it is the positive ion, the lithium, that actually shuttles between the electrodes and gets stored. When a visual here is a true simulation, we will show it. When it is just a helpful sketch, we will say so. Now the most important idea in the whole episode. These 2 currents are locked together. For every electron that leaves through the wire, exactly 1 lithium ion must cross the inside. They move in perfect lockstep because charge is not allowed to pile up anywhere. And that has a startling consequence. Cut the outside wire, and the inside stops instantly. No electron can leave, so no ion can cross, and the chemistry simply freezes. That is why a battery can sit in a drawer for a year and barely drain. With no complete circuit, neither current can flow. And when an ion finally reaches the far electrode, it does not just pile up on the surface. It slips into the solid structure of the electrode, and an electron arriving from the wire meets it right there, at the very same spot, keeping everything balanced. Ion from the inside, electron from the outside, arriving together, We will spend an entire episode inside that structure later on. So strip everything away and a battery is beautifully simple. Two currents. Electrons on the outside doing the work you actually want. Ions on the inside, quietly carrying the charge back. They meet at the electrodes and the whole thing runs until one side is full and the other is empty. The concentration, the voltage, the current, everything we just glimpsed is one hidden layer of this same cell. Over this series, we are going to light up every one of those layers, one at a time, on this exact cell. Next time, that sagging voltage line is not just a number falling. It is a story. And once you can read it, you can read a battery's entire chemistry off a single curve. This was the battery simulated. Episode 1.